So before I start, let me just quickly announce one thing, that if you have noticed, anyone looked at the title before of the talk I was supposed to give, or which was mailed, actually there's a change in the title. It's about macroscopic superposition of quantum states and experiments towards that. This is the first week, starting week of the experimental, starting day of the experimental week. And I'll not be talking about feedback control. And that's basically something which was initially the plan, but in the first week of the school, it kind of appeared that most of the students are theorists. How many are experimentalists or interested? Oh, wow, that's a good number. So maybe the theorists just didn't show up. Otherwise the plan really, I have one transparency on feedback control. The plan really was to talk in details, the nitty-gritty details of what we mean by feedback control and how we really do things. And for experimentalists, really, that's really our main technique. It's like the field theory for us. But just felt that, for theorists, it will be really a pain to sit for 1.5 hours. So that's one of the things. And then just to put it in perspective, this is Angelo's slide, last slide from last talk, so just to have a continuity. To be honest, from right in the beginning, I want to mention another point, and that is that for this school, I am as much of a student as all of you guys, because I'm really not, we are really not in a position yet to ask questions of the, like the validity of quantum mechanics. As we are having a dinner chat a few days back, and Angelo was mentioning that, you guys experimentalists, you are 20 years behind, and that's what it is. We are basically at a state, most of the community is at a state where we are still trying to create stable superpositions of quantum states, making sure that we understand that there are superpositions, and trying to see how to scale that up to larger objects. So we are really far, but the only thing that motivates us actually in every day is that we know that, one day any of the experimental groups anywhere in the world, if they actually find a deviation or see a new physics, then actually for theorists also, all 20 years ahead work is destroyed and everything is reset to zero. They'll have to follow what the physics is guiding. So in perspective of Angelo's work, basically he was, or Angelo's graph, he was talking about various different kinds of systems when he talked about non-interferometric experiments, and I'll be talking about, in these cold atoms and something which is very close to cantilevers. These are nanomembranes. This is a system that's just starting to come up. These are actually atomically thin membranes which are called graphene. They are hanging and vibrating, so very similar to the cantilevers. And there the question is whether you can create superpositions and stable superpositions and so on. I'm not sure whether I'll have time to get to this, but I'll just at least mention what are the activities going on in terms of experiments. And one last point before I start is that I really apologize. I really hate to actually give a transparency talk in a school, but this is just a one talk series. So this is like a first talk of a course where I'm supposed to give you an introduction of what's supposed to be there, and this is also the last talk. So this talk will be a series of pointers where I'll point towards things that I find interesting and things that the community finds interesting. And then the idea is that, like over next 2 weeks, you will be here, I'll be here. So if you find anything to be very confusing, very interesting, you can find me always and we can discuss. So with that, let me just restate, like what really, so this is the problem with the math. But I can write it down. So, it's already having issues in translating things from the Windows machine. So really what I'm talking of for macroscopic superposition, really the goal of the field is to actually create here this states which we call the Schrodinger cat states or Noon states, which are basically of this form. There's some phase where A and B are just two modes. So basically to create a quantum state where you have n particles, it's a macroscopic quantum state where n is supposed to be very large, and you create the state such that either it's at a position or at a particular mode A, all of them, or at B. But more importantly, it's not just classically the bottle being here or there, but actually it's a coherent superposition with the most important term being the relative phase between them. So the question is, can one actually create this kind of superpositions? Is that going to be stable? Can one actually, is it going to be stable enough to take measurements? And then one can actually really go ahead and ask more interesting questions. So that's really the point. Noon state, basically. So this is a macroscopic superposition. So noon, from here. Well, in a cat state also, right? So normally the way it's done is, the cat is, I don't know, cat is dead plus alive. So this is, usually it's written, but it's assumed that there is a phase factor, or as an experimentalist, the only way we can check that there is a superposition and it's not an incoherent mixture of the cat being dead or alive is by changing this phase. So in our lab, I'll talk a few examples of that. In our lab, when we are actually checking a quantum superposition, what really matters, what really distinguishes classical from quantum superposition is really that phase. So we need to have a control on the phase. And for Schrodinger's ideal cat, this phase is basically coming from that decay rate, which actually sets up a macroscopic phase between these two states. So before I start, since anyways it's a tutorial, I'll just have, I have just two small little questions as quizzes you can take just to calibrate, where we stand and what is your background. So first question is, like in Professor Sorkin's lecture, you have seen a lot of beam splitters. I don't know if you are already aware that when he was writing those split states, he was writing, one amplitude to be I over square root of 2, the other to be 1 over square root of 2. Everyone is familiar why it should be, there should be a pi over, okay. So, so that's exactly the situation. So, so you can imagine that this is basically a partially silvered mirror, light falls, let's say 50% of the light goes one way, 50% of the light goes other way. So now the question is, suppose I actually start making the light weaker and weaker to a point where on average within a time frame, 1 photon falls on this splitter. So the question is, what will happen? Anyone? Yeah, but so superposition of what? Transmitted and reflected, so it's basically a superposition with 0, if that's what you're saying. So what he's saying is that, the state you're going to see is that 1, 0, plus 0, 1, again with a phase, which in particular case you can choose this to be pi by 2. And this 1 is, so this 2, here the labels are basically the 2 ports of the beam splitter, right? But actually, if I actually take a measurement, if I put detectors at this ends, what am I going to see? I'll see 50% of the time the photon comes this way, or 50% of the time the photon goes that way, right? So, so that's what realistically I'll see. Finally, these are like billiard balls. They cannot split up into 2 parts, right? So the superposition is there, but finally the probabilities are basically half out. So now the question comes that suppose now I just make the light a little more powerful so that there are 2 photons which are actually falling on this. Now what is going to happen in terms of the probabilities? Okay, you're already giving the answer. Normally, if you think in terms of the probabilities, what would one expect that there are, like 4 cases, either both the photons go this way, or both the photons go that way, or 1 photon goes this way and the other photon goes that way, and it can happen 2 ways. So 50% of the time, you expect that 1 photon is going this way, the other photon is going that way. It's coin tossing, and the rest of the time you expect the 2 photons either going this way or that way. But interestingly enough, if you actually just use those amplitudes and do this calculation, you find that you do find the amplitudes for the two photons either going this way or that way, but the case that you expect most probable, that one photon going this way and the other photon going that way, that case doesn't exist. You know, so this is a very, very simple example of kind of a superposition that's playing something very interesting. This was actually first time predicted in 1986 by Mandel, and the experiment was done by three people, Hong, Wu, and Mandel, and it's a very, very well-known, in fact, one of the classic examples of how our intuitions, if our single photons or single particles can completely go wrong. It's also a very nice and classic example of, you know, a state that I was writing there, but at a very, very low level. It's nowhere close to a cat state or a macroscopic superposition, but it's really more of a kitten or a baby kitten. Yeah, so basically, like in the simplest case, I'm saying that, you know, I'm talking of a 2-photon Fock state. But then when you're talking of the gaps and so on, basically there's a wave function associated with that, right? If I project it in real space, there's a wave function associated with that. So if I actually keep increasing the distance, at some point, you know, there's a coherence length. So there's a particular length scale over which they'll actually look like a 2-photon wave packet, but after that it will stop. In fact, that coherence, basically why this result is really, really surprising is because on one hand, the photons are particles, but at the same time, they inherently are waves also. And that wave property is what cancels this one photon probabilities, whereas the particle properties are what you would have expected to be here. No, so you'll have to, so basically, you know, if you are going into the details of coherence length, then the 2-photon wave packet, that actually needs to be smaller than the coherence length. This part is basically exactly the same as that of classical optics, that you see interference only within the coherence length. So basically the photon at the same time is carrying its signature of particles, and you will see counts, and you will see probabilities, coin tossing like probabilities, but it's also carrying its information about the coherence length. Yeah, otherwise this would happen. Yeah, you see this all the time. This is all in real space. You're talking about the fact that if I'm thinking in terms of a wave packet, how do I think in terms? So basically, one way of thinking about it, a very simple answer is that, you know, there are definite energies, but actually there's so when you have a wave packet, it has a spread in time, so it has a spread in frequency, and that delta omega is much, much smaller than omega naught, right? And if you want to be more careful, there's this whole point that when you're talking of just a single photon with a specific frequency, you're talking of a continuous wave, like, you know, which is not changing. Otherwise, what is happening is as you are trying to give time shape, you're adding more and more modes. So that becomes like multi-mode quantum optics. And you basically need to write down so, you know, like basically this photon in truly in nature has like all these different modes of frequencies which add up to give you a single photon packet. So there's a very well, like, you know, very solid formulation for that. So second quiz. This is comparatively a little harder. So we know about atoms. So this is how I'm depicting an atom. So, you know, this is the atom. To remember that, you know, there's one atom I'm talking of. This is the ground state. This is the excited state. Suppose the atom goes to the excited state, and from the excited state it can decay, and decay in a time scale, the inverse of, like, which we'll call the lifetime, you know, the inverse of it is the line width of that state. Let's say that time scale is t. Right? This is a scenario which we'll use several times in this lecture, and this is something everyone is aware of. Now consider the situation where two such atoms are there. You know, two such atoms, both are sitting in the excited state. And also, I'm not talking of like superposed atoms or anything, because these atoms, let's say, are very, very far apart. They are like, let's say, 100 times away from the de Broglie wavelength. So actually, there is no wave function superposition. So now, suppose one of these atoms decay, or I ask the question that what is the lifetime of this atom? What do you expect? Huh? What is the characteristic lifetime of the atom? So if it's T for one atom, now that there is one atom and very far away I have put another atom, 100 times the de Broglie wavelength away, what would be the, is it going to affect? It should not be affected, right? So that was the kind of the notion for a long, long time, like, you know, like for a long time, if you would have even asked this question, people would have said, you're crazy, that, you know, how can it affect if the wave functions are not overlapping? But it turns out that actually in this scenario, and I'm repeating that it's 100 times the de Broglie wavelength, in this scenario, actually the lifetime of this atom, what you will measure in the lab will be half of what you would have expected. And this is a very, very, again, a surprising result. This is, again, another example of such, you know, very baby superposed states. No one really expected that. And it turns out that normally you would not expect it because you know, the normal quantum mechanics says that the atoms are not superposed, but actually there's something more going on. They are actually emitting a photon. I'll come back to more details of this. And from the photon's perspective, whose wavelength is very large, a photon is very large in size, say micron, so it's like 1,000 times larger than the atom. From that photon's perspective, you cannot differentiate which atom actually emitted. And that lack of information puts these atoms in that kind of a superposed states, but a very baby superposed states. Identical atoms, you know. And you actually see that very, very strongly, you know, I'm an experimentalist, it's like the things I see, I believe. This is something where you see actually the lifetime of the atom changes, it gets modified, and this is something which was again much later in late 1960s, was pointed out by Dickie for the first time. It was a big surprise, but people right away started seeing that experimentally. So these are kind of the tools I'll be pointing out for this talk to show like how people are kind of trying to go towards, like experimentalists are trying to go towards creating such macroscopic non-trivial superposition. And then the question is, how far can we go in terms of that? Yeah, so if the atoms are, actually the limit turns out to be quite non-trivial. So normally, this particular case, one can right away say that, you know, if the atoms are farther than the wavelength of light, the wavelength of the photon that they're emitting, in that case you can differentiate between the two. But it turns out that there also there is some very interesting things that spatially there is an asymmetry that's, and in particular directions you will still see that, you know, like for example, if these are the two atoms, they're far apart, but if I put a detector here such that I really cannot separate the two atoms, there also I'll see, you know, like the same kind of what is called super radials. Exactly, yeah. I'll come into more details, exactly. No, they are not. They're coupled only through, so basically that was the Dickie's point. The whole coupling is coming because they are actually interacting with the same radiation field. Yeah, but there is no direct coupling. Yeah, there is no interaction, right? Because the atoms are actually in the excited state, and they are basically sitting in vacuum. It's a different question that, you know, like then one needs to go into the fact that, you know, why the atoms are decaying at all from a stable eigenstate, because of the fact that they're actually seeing some common common vacuum modes, and that, well, that's the coupling which is basically is causing it, but it's a coupling to the radiation field, basically. And to start with, the radiation fields are empty. They're completely vacuum. So it's not that I'm putting in a light to force it. So with that, let me just outline the talk. Or rather, it's kind of a talk that it's a little ambitious. Wherever we'll go up to whichever point, I'll stop there. So first, I'll start with the basic notion of what we mean by superposition of atoms, like a single atom. We all have done some sort of atomic physics starting from 12th standard. We know that atoms have discrete levels. So and you send in light and you see this absorption spectra, discrete absorption spectra. The question is, like if I say that I have created a superposition in the atoms, experimentally in the lab, what is the signature you're going to see? How is that spectrum going to change? So we'll start with a single atom. From there, we'll go towards, how many atoms we can actually try to superpose and, whether those kind of superpositions can eventually lead to this kind of Noon states or macroscopic superpositions. And then finally, I'll talk about some of the experiments we are doing, and there's a lot of people are doing similar things about, like, actually starting with macroscopic objects like, membranes and so on, and trying to see whether you can actually create stable superpositions and how do you measure those superpositions, what is the meaning of those, and basically the main point of all this being, what do you see in the lab? Not what we write in the board, but, what is it that actually makes this thing. So, just one point, since now it seems like there are a lot of experimentally interested students, that actually the talk was supposed to be feedback control, because that's pretty much one of the main things we do every day in the lab, and that actually is a field which is very rarely discussed by physicists, but it's superbly exciting, and it's basically the idea of the field goes like this, that any of the systems, whether it's a classical system or quantum system, you can actually think of the system as an input-output formulation, that you are actually driving the system and you're looking at the output. But if you want to do it stably, you will have to make sure that it's not being disturbed by environmental issues. So you will normally find that there is always environmental noise that's coupling in, and that's basically taking the system away from what you want to see. So what you do usually is you take a small part of the output of the system, and keep watching it. And as the system is starting to deviate, you basically, that by watching from the output, you actually do some adjustment in the input so that, it comes back to the same point. So you basically control it, so that the system stays where it is. And this is actually a field which is purely developed, and it's an extremely intense field in the field of electrical engineering. It's called control theory. And starting from, in this room, the temperature is not running away, the air conditioner has a feedback, to a point, actually, like some of the most exciting things that are happening in this field of classical control theory are this, I don't know if you follow this unmanned, control of airplanes, where or self-driving cars is a great example of control theory, where, Google has now, and many companies have self-driving cars where they actually see humans, people everywhere, and accordingly control. And, like you can actually get it driving. So all of that is control theory, and that's the same theory we use every day in the lab to actually hold these atoms, like interrogate with them for long times and create the superpositions. So that's that for feedback control, but this is not a talk on feedback control. Let me get back to the general question that I was asking, that, we know atomic physics, what started like 100 years back, that people would take a vapor cell like this, literally a glass cell where there is some atomic vapor. You send in light through it, and you see that as you change the frequency of the light, there are certain frequencies where people started seeing discrete absorptions. This was a huge, huge surprise 100 years back that led to Bohr's theory, that led to quantum mechanics. But then there was another surprise about 50 years back, when lasers were discovered, when the coherence length, people had better light sources. One thing they started observing is that the well-known resonances that were already there, so this is an example of that very early on, that this is kind of a resonance spectra that you're looking at. And when you actually have, people started using these very well-controlled light sources like lasers with well-controlled polarizations, people found that certain resonances actually were missing. They call these dark resonances. So this is, you see these dark lines. Missing as in, you see that basically, basically in those resonances, light is not being absorbed by the atom. Suddenly the atom decides to not to absorb it. This was also, at that time, people had some explanations. There's a very nice, I'll send some of the slides so that you can actually look at this. So this is the kind of the father of this field of dark resonances, Coherent Phononics. His Nobel Prize actually goes for this also. And he recently has written a very nice review article which you can look at. So the question is, why these lines are missing? It turns out, and that was what eventually got Coherent Phononics the Nobel Prize, that, like to understand this behavior, you need to remember that atoms are really not just two levels with a ground state and an excited state, but to start with, atoms have spin and so on. So for example, the ground state has it's actually a manifold. It has like many different states. For example, what you think as a single ground state, if you put a magnetic field, you will see that it splits up into many levels. So basically to understand this, just consider like two states of the ground state manifold. There are two such states. And then the other part is that, consider two optical fields such that they are both resonant to a same excited state. So there's so this field is resonant from 1 to 3. I've labeled them 1, 2, and 3. This omega 1, you can think of them as the field strength, and nu 1 as the frequency. So this is coupled here, that is coupled here, and the couplings are very simple. They are basically, they are just, you can very simply write it as D dot E. If you are more theoretically oriented, you can say that, basically the electromagnetic field has a momentum that changes the momentum. So it's P dot A, and under certain Coulomb gauge, it's exactly equivalent. So basically there's a dipole moment that's induced, and that dipole moment is basically coupling to the electric field. And then how do you think of this dipole moment? It's basically the separation of the charge. So you can actually expand this in terms of the states. And you find that this is because this is an odd operator, there are only cross states that you can expand to. So basically, I can write down an effective Hamiltonian describing this process where, you see that there are these two terms, omega 1 being the strength of the field times the dipole moment. So you see that this term is effectively this term, except that, there are the states, there is no state like 1, 1 or 2, 2, there is 1, 3 and 2, 3. They're physically very meaningful. Omega 1 term is saying that the term actually makes the atom make a transition from 1 to 3, and then the Hermitian conjugate brings it back, and similarly omega 2 actually couples it from 2 to 3. So 1 and 2 are basically just two states of the ground state manifold. So they can be like, they can be different energies, but for example, they can be just Zeeman sublevels, or they can be hyperfine states where, they are very close by. They're ground state, so they're long-lived. That is what I mean by ground state. And they can be degenerate in energy. For example, they can be like just characterized by their respective nucleus spins. So that, and then, this part is kind of, some of you might be finding it disturbing. This is just reminding ourselves that the excited state actually has a lifetime, what we talked in the beginning, so it decays. So if you see, I intentionally put this, which basically is a non-Hermitian term, but which basically makes the Hamiltonian, not conserved, which is the meaning of this decay, basically. So, but now there are two fields, and you can actually look at now this slightly differently. Physically, you can see that actually the state 3 is now just not coupling to 1, but it's coupling to 1 and 2. And it's also coupling to 1 and 2 in a very specific combination. You see that actually it's a superposition of 1 and 2 with these two fields with 3. And so this is the state that's actually coupling. So physically, it's not 1 anymore or 2 anymore, but it's a very specific combination of 1 and 2, right? So, so now, so that's all you need to understand these dark resonances, because right now right away you can say that this is a very specific superposed state that's coupling to the excited state. So if I actually can make a state which is orthogonal to that state, which what I mean by this is a state which I'm calling D for dark, which is basically, you see that I have just interchanged these coefficients and changed the complex conjugate so that, this state is dark. With that, if this Hamiltonian actually operates, there is no transition, which is basically saying something very spectacular. It's extremely simple maths. but the physics is spectacular. It's saying that in presence of these two fields which are completely resonant with the atoms, the atom basically is not willing to go to the excited state because it's just is going to a state which is completely orthogonal to the dark state, right? So that's one thing. People also realize that there are way more significance to this state. For example, because now this is a superposition of two ground states, long-lived states, it doesn't have any excited state component, right? And as a result, if you can create such a superposition, it will live for a long time. So why time is important for us? Because we would like to take measurements. We need to have enough time to actually take measurements. So you actually see that, like it can stay for a long, long time. So there is no excited states. And then there are implications in quantum information and quantum optics that, what we call noise, what actually scares experimentalists from thinking of even single photons is actually this spontaneously scattered photons. Like, like you buy a single photon detector and you turn it on and there are scattering of photons everywhere and that's it. You cannot stop it. You see that spontaneously scattered photons are basically scattering from excited state. So you see that actually this process completely suppresses excited state scattering. In fact, this is a very, very big deal that way, that this is one very important process which stops it, and as a result, this kind of states forms a backbone presently of atomic physics, optical atomic physics-based, quantum information processes and so on. But there are, but let's come back to the ground level, that experimentally what would you see? We know that, like if you actually normally see this resonances, you will see these transitions, you will see kind of a line width, so you will see this line, it will have a shape, Lorentzian or something. So, but now, this is what you expect, that, if you just probe, for example, with the blue light, you will actually see that there is a line width, there is an atomic transition, this is what we would call the line. But now when you turn on this is exactly what will look like, if you actually go ahead and solve the Hamiltonian, write down the wave function and write down the response, which are also very straightforward, you will actually find that right where otherwise the blue light had maximum absorption, in the presence of the red light, the condition under which this dark state will be formed is right on resonance. So where you would have expected maximum scattering, you suddenly see that there is no scattering. There is no absorption. And that's why those fluorescence lines, they were dark lines because the light was not being scattered at all by the photons. And this is the point, experimentally, is what you would be looking for the superpositions. Any questions up to this point? This is really, really a very, very important point, which I'll use all through the talk. Okay, so I'm talking very simple things, so. Yeah, so there's another very important point of this thing. I can give like 2 lectures just on this superposed states. There's another very interesting thing, and that is you see that this is a superposition, a true quantum superposition. You see that through this, cancellation of absorption or cancellation of scattering of photons. But also you see that what are these omega 2 and omega 1? These are actually the strength of the optical fields that I'm putting into the system, right? So this you see, like, as experimentalists, we are constantly, like, we get very nervous when we, when we are writing down hypothetical systems, because we are really control freak. We really want to have knobs that we can control. And suddenly you see that this is a superposed state which actually has 2 knobs, in fact, 2 these are actually things that I can control. I can actually just control the intensity of the 2 lights, 2 optical fields, and that way I can actually control the amount of superposition. In fact, I can, by controlling the relative phase between these 2 optical fields, I can actually control that very important phase phi, which is absolutely necessary to prove the coherence. I can actually control that. And more importantly, there's a very nice physical side of it. You see that when omega 2, by the way, you see that there's kind of a anti-symmetry, there's a kind of a opposite symmetries. You see that this field omega 2 couples to 1 and omega 1 couples to 2. That was kind of the point for making the state orthogonal, right? So if you remember this will be very useful for some of the parts, that there is kind of a non-intuitive coupling, reverse coupling. But also another thing you see that if omega 2 is very small, the dark state is mostly 2. And if omega 1 is very large, the dark state, omega 1 is very large, I'm saying the other way around. If omega 1 is very large, the dark state is mostly 2. I increase this and the dark state becomes that. So these are just points that will actually have a lot of physical significance later when I'll talk about the actual experiments. So that's it. So we are saying that, right at that point, if you turn on these lights through the vapor cell, you will actually see that, there are the superpositions. But what about classical processes? If I'm now starting to think more carefully about it, I can say that, if I actually think of this atomic vapor, there are like, atoms are actually roughly, the room temperature velocity of atoms are like 300 or 400 meters per second. They're extremely, they're zipping, like fast, they're just really, really fast moving. And so then the experiment is the following, that I'm actually sending in light or 2 light fields. So you can see every atom is staying for a short time, right? It's going away. And even if it interacts, and suppose there's a superposition, and I'm claiming that the superposition is long-lived, but it's going to go and hit the walls, and that's like banging on the head, it's going to reset. So these are all classical processes. There are more fancier, non-trivial classical processes, which are called optical pumping and so on in the systems. So basically, in presence of all this, what about this superposition? So this is slightly technical. This is an, Yeah, so basically you see that that particular point where it's on resonance, that's where you saw that, so that's where it completely becomes transparent. So that point basically means that, whatever your frequencies are, both of them are on resonance with the excited state. So that's the relation basically. So if these 2 states are degenerate, then the nu1 and nu2 are exactly same. If they're non-degenerate, their differences are exactly the separation. Yeah. So this is an experiment that we did recently at IIT Kanpur, where we were basically asking this question, that what about the classical processes? There are all these systems where there are many other things happening. So how do we even differentiate? So we see something where there is some transparency, and but there are also these classical processes mixed. So this is kind of just to give you a flavor. It gets a little technical, but just to give you a flavor of how these experiments actually look like. So this is actually a vapor cell. These dots are basically trying to remind us that atoms are there, but also you should remember that they are flying past really, really fast, 300, 400 meters per second. And then here, this red line is the line where we actually send in these 2 optical fields, and the rest of it would have been the subject of the original talk, that, you need to, just you asked about the frequencies, so you need to be very accurate about the frequencies. You cannot let the frequencies to drift out. So a lot of control theory in terms of controlling various of these things, but those are not the main point now. The point is, how is the quantum superposition forming? When is it forming? Is it at all forming? So when we actually do the experiment, let me not go into the energy level details, this is how it looks like, So one of the, besides this dark state being a major theme for what I'm talking, another major theme is that, this control, that how, we buy things from the market, we set up an experiment in the lab, these are all classical. How do we finally eventually go and see some quantum states? So this is just to convince you that this actually look like metals and everything. This is the experiment, this is the cell, there are lots of magnetic coils to cancel magnetic fields, but effectively these big things are objects to control the polarization of the light, and the light is going this way, and these little holes are through which the light is going in and out. And we basically, to answer this question, we don't look at, this is what the field people have been looking at for 2 decades and trying to see the superposition. We actually didn't look at frequency space. We decided to, because we are asking dynamics questions, that how the superposition is forming and how that is competing with classical systems. So we basically started looking at time snaps. So we would basically send, keep repeating the experiment several times, small pulses or instances, and we would ask the question that what is happening to the atom now and then and after and so on, right? So so we would actually, do a series of experiments where there are these little pulses, and would take the envelope of that to see what happens. And what we find is something like this, that, just to quickly take you through the graph, So this axis is time axis, and things starts happening at t equals 0 that we are defining here. Before that, so this part is transmission of light through, right? So you see that there is a certain amount of transmission, 0.4 or 40% transmission, because of the fact that there are atoms who are absorbing the rest of the light, right? So this is what you would have expected for a simple two-level atom, light going through the thing. At this t equals 0, we actually turn on the second light. So right at that point, basically suddenly the system is supposed to go into the dark state, and a lot of light should go through, because you know the atom is failing to absorb or refusing to absorb the light. And that's exactly what we see, that there's a sharp rise, and then there's a fall, there's all this like kind of strange curves, then it kind of tries to settle. This is the point we turn it off. In fact, we see that immediately it goes down, because you know we turn off this second field, so it should have come back to this level, but we see that it's actually not going all the way, like it's actually going way below, and then it comes back slowly. So the question is, what are the meaning of all this? And that makes this a little bit technical. It turns out that there are very, very interesting physical significances of all this, and that just this experiment is not enough. In fact, you know, you can actually simulate this system, where the simulation is also kind of interesting, because this is a coupled system where the atoms are basically governed by this kind of Hamiltonians, and they have decays, this Lindblad forms, and the electric fields are governed by the Maxwell's equations, but they're driven by this polarization, which is basically set by the atoms, and the atoms are driven by the electric fields, which are set by this. So you see that there's a coupled set of equations you solve, and you find the same kind of behavior. But because it's a simulation, now you can look at like various different elements, and by looking at that, what we find is something very interesting. We find that actually, you know, you see that there's a very sharp rise, and this sharp rise basically tells us that the moment you turn on the second field, immediately the system is actually going into a dark state, or it's actually going into a superposed state. But the classical processes are much slower, and they kind of wake up after a while, and they actually say that no, we'll not allow the dark state. So they start competing and actually starts bringing it down. In fact, if you have too much of this classical processes, then they'll actually bring it completely back, and you will not see any kind of transparency. And then here, actually, when we shut it off, this fall, it's going down. It can go way below where we started, or might not go that much. This fall length, what we find in the lab, is a great measure of how much superposition of the states you have, basically, in the system. And eventually, there are also very interesting things of the fact that there's a slow rise, which is basically a signature of the atoms, like, you know, zipping past this millimeter-sized beams at 300 meters per second. And you actually see these are basically time traces of the atoms zipping through that. You know, so so we checked this for, you know, like highly quantum superposed state, 1 minute. Highly quantum superposed state, not so quantum superposed states, which people would say open quantum systems, closed quantum systems, and completely incoherent systems. And you find that, for example, this is a state where there is no quantum superposition, but we artificially created a transparency window. And for people who are like, you know, in this field, this is also something very well known in atomic physics. You can create such transparency windows called saturated absorption spectroscopy, and in those cases, you don't see this kind of things. Yeah. Going up. So basically going below this level. So it's basically like, you know, like when you shut it off, there's still enough coherence to bring it down. So it's actually induced absorption. So the system is off, but you know, like whatever the atoms are there, there's still some superposition, and actually some of the atoms are actually just gone because of the fact that, you know, like there are these two fields working, so the atoms are basically moved from here to there, and there's some resultant superposition. And as a result, what you started from here and this part is not the same. Or rather, you know, simply speaking, we can talk in more details about this. There are like, actually, like why I'm hesitating into going into too much details is because I have not talked about a very important part that is playing a major role here, which is optical counting. You know, and that I need to explain then. But all I can say is that, for example, this is an open quantum system where the superposition is not that much, and you see that there is a fall, but that fall is like halfway, right? And here you see that this is a completely incoherent system, there is no coherence at all, and you see that there is absolutely no fall. You turn it off here, and it slowly kind of, this is the atom strength. So that length is basically a direct measure of the amount of coherence. So more details are there here, but this is kind of a very textbook example of, how to understand how the superpositions are forming. And besides the fact that this kind of superposed states, people have used to do like many spectacular magical physics. For example, you have probably heard of slow and stopped light. This actually hit the, Lenahau's experiments in 1999. That was with BECs, but later there were these experiments done in hot atomic vapors, where you actually create a system where light actually travels at the speed of like 17 meters per second was Lenahau's time, like 10 meters per second, and so on. It really slows down. And people were really like, amazed by that. But actually the physics is again very simple, that this is the absorption. So if you're familiar with Kramers-Kronig, absorption is directly related to refractive index, so it's related to the velocity. So this sharp change in absorption also causes a very steep change in the dispersion. And the group velocity actually has a rate of change of the refractive index as a function of omega. That very steep change actually just reduces the group velocity of light. And you should remember that this slow light propagation, there is nothing special about it. It's basically the light is interacting with a medium. So what we are calling slow light is really not a, not really light itself, but it's actually light coupled with atoms. So it's something like a polariton, and that velocity is extremely, extremely slow. And then the same thing you can actually use to stop light and store light for a while. I'll talk about that a little bit. But coming back to this, the whole promise where we started with is that we would like to create macroscopic superpositions. And you can see that that is inherently problematic with hot atomic vapors because, again, if you think of this light that, like there are atoms, there are many atoms which are interacting, but they are going in and out of the system. In fact, everything I talked about till now regarding the dark state, if you see, that is actually a one atom physics, right? Like it's basically things happening inside one atom, right? So if I'm actually thinking of creating macroscopic superpositions, this is definitely not a great system to look at. So that's where, like usually people working on macroscopic superpositions would move to cold atoms. So now my next few slides are just a extremely naive and simple-minded introduction to cold atoms, like how do you cool? You basically start with a vapor which is of atoms, the atoms are Maxwell-Boltzmann distributed, moving at very fast velocities, but you use the fact that, when they're scattering photons, photons are massless objects, but they have momentum. So no matter how small, every time the atom scatters a photon, it also gets a momentum kick. And the momentum of the photon, we all know, when we are writing photon, even classically as e to the power I k dot r, there's a k vector, and that's really quantum mechanical is the momentum of the photon. So, if it absorbs a photon this direction and emits a photon that direction, it gets a resultant kick this way. So, again, with the advent of lasers, people realize that, though an atom might actually get a tiny, tiny little kick from a photon, but, like lasers actually provide you with a series of identical photons. So you can actually repeat that process many, many times, like billion times, trillion times. And as a result, those little momentum kicks, if you actually have proper control, again, all of control theory, that if you can keep the lasers at the right frequencies for a long time, the atoms will be forced to see the same photons, will scatter like trillions of photons, and eventually a 500 meters per second atom will start slowing down, and like because it's losing its energy, and it will slow down almost close to zero. So that's kind of the principle of it. And these are basically saying that, you need to do that, from different directions, because the atom actually can move in any direction, which I can think in terms of x, y, z coordinates. So I need to cool it down in phase space, basically. So another way of thinking of it is, it's the same thing that. So technically the way it's done is that you force the atom to absorb a photon of slightly. Suddenly this volume went up. So you make the atom absorbs a photon of slightly lower energy, but it emits a photon of that from its resonance. So basically that extra energy it gives from its pocket, and that's what the energy it's losing. So that's one part of it. But that energy loss is exactly like friction. So it's basically a frictional force. It takes away energy. But there's a difference between frictional force and trap. Right? A friction really cannot trap. For example, just imagine that there's a frictional surface and you throw a particle. If the particle has a certain velocity, it will actually just go through. It will lose energy, but it will come to the other side, right? You really cannot trap. So actually to trap, you need another element, which are called this, which are these magnetic fields. You are using the principle that atoms are also tiny little, they're like tiny little magnets, they have spin, and as a result, they will sense magnetic fields. And if you can arrange the magnetic fields properly, such that when the atoms are trying to move away from a point where the magnetic field is 0, from that point, if it tries to move out, it sees a magnetic field gradient and it starts experiencing a force, then the atoms will be actually confined in that region. So basically, in the lab, you create a place where you have all these lasers intersecting at the same point where there's a magnetic trap. So the atoms which are moving fast, the moment they try to cross that region, they actually start losing energy. And on top of that, the magnets are trying to push it in a localized region, and you actually get an extremely cold, cold cloud of atoms. So that's, this is our setup, extremely crude looking. Everything is like put together, very ghetto, home built. So what you're looking at here, this glass cell, is where it's a very high vacuum system, ultra high vacuum. So these are like 12 to 13 orders of magnitude lower in pressure than the room temperature pressure. And then these are like just coils, Helmholtz coils wound to like, make the trap, magnetic trap. And then there are, this cubes you see, this circles you see, these are like controlling polarization and sending light from all 6 directions, or rather 3 directions, x, y, z, and minus x, y, z. And when you do everything right, and when you can control the system properly to actually so that the, the photons are similar and they are all the time locked to a particular frequency, they are not drifting away, you actually see this thing, which is basically, this white thing, which is very large in size, but actually it contains an extremely small, that way, number of atoms. It actually contains about 1 million atoms, 10 to the power 6. Which is very large compared to, if you compare to a single atom or few atoms, but it's very small compared to Avogadro's, right? So anything that we see has Avogadro's number of atoms, but this one actually has like only like several hundred, like orders of magnitude smaller than the Avogadro's number, but you still see that to be very large cloud. It's kind of a cloud of atoms. What you see is basically the scattered photons, and you see that because the scattering cross-section of the atoms are of the order of lambda square. So actually, if you see optically an atom, that's very large. So and also, by the way, like normally you can see this naked eye. If you come to the lab, you will see that like directly right in front of you, standing there. And this is one of the coldest thing you can ever see. Like this is. It's way cooler than deep space. It's much cooler than like what people can do with helium. The temperatures are of the order of like 50, 100 microkelvin. You can, with other species, you can go even lower. And also, you can actually, these are all radiation pressure basically, like the optical fields. So you can actually play interesting games. You can actually, create situations where there's so much of radiation pressure that the atoms are basically repelled from the center, and then they form this beautiful geometric patterns like rings and so on, and basically these are like atoms like moving in a ring, and they're crawling at 3-4 millimeters per second. Basically, they're just like, and they're held by the magnetic field, and this is all, by the way, everything else is at room temperature. Just the atoms are at so low temperature because they're not thermalizing. They're basically like never seeing the walls, so they don't know what is the temperature. This is a gas. This is still a gas. So the bound state will call when we push down this further to another like 2-3 orders of magnitude, like in the range of nanokelvin. Then the de Broglie wavelengths will superpose, and they'll form a BEC. And so that is like the ground state, like a new phase. But that's something which is inherently a many body state, n particle system. But everything I'm talking of are actually still gas molecule, they are still an ideal gas-like thing, so they are still separated, their wavelengths are not overlapping, but exactly that quiz 2 that I was asking, that's exactly what we'll be using to show that, they actually form still very interesting collective states. So now the question is, where the atoms are, and if you see the atoms are, so this is a little bit more technical that, these are showing explicitly the ground state manifold of a particular hyperfine ground state manifold, and you see that there are all these different spin projection states, and the atoms are basically, when you are pulling them down, they are basically everywhere on that. So the next step we do to kind of get to a collective state, so I'm now going step by step. The next step we do is to actually, so you see that the meaning of this different projections are basically that the atoms are all pointing in different directions. So you can actually start putting these atoms all in the same state, right? And that you do by, it's just, what happened? So, you basically, these are all again, for the experimentally oriented people, these are all time domain measurements where, where you are basically trapping the atoms. Then to prepare them in a specific state, you can see that you cannot really afford to have any magnetic fields or stray magnetic fields, so you'll have to cancel all those magnetic fields and, make a perfect zero and so on. So you do that, so you cannot afford to have the magnetic trap, so you turn these things on and off and so on, and in between you send these very short pulses and prepare the atoms in a specific state. And when you turn off the trap, these million atoms, they are basically free falling, but they are so, and free falling because of gravity, which otherwise would sound senseless, but they are basically zero velocity, so they start seeing the gravity. But they're falling very slowly in the experimental timescales of microseconds or nanoseconds, so you can do many things with them before they fall down from your optic field. So this is kind of really just to give a flavor that, it's all like a series of time sequence, and you basically send in other optical fields when after the traps are off to actually create a spin polarized system. So you actually prepare them all in a specific ground state, and you see the signatures of that. This is kind of where we are experimentally, but I'll keep going and telling you about how they form a many-body state from some experiments earlier that we did, not in IIT Kanpur. And it's the following, right? So basically now you can ask the question that when we have spin polarized them very well, a million atoms, they're all like that cloud you see. Now you should imagine their internal spin structures, so they are actually all pointing in one direction. And now I do the following experiment. I come with a light field, which is very weak. So it's basically, incident on this, but it's very, it has, let's say, 1 photon per microsecond. So, so it basically can scatter off, 1 photon can scatter off only 1 atom, though there might be a million atoms. And when an atom scatters, it comes to a different spin state, right? So it goes to the excited state and comes there. So this is the scenario, and I can detect that photon, right? So basically, this is a cartoon of that kind of a cloud of atoms, and basically so this is something, I'll come to this Dickie's paper. This is that seminal paper that actually talked about this kind of collective states purely because of light projection and measurements. So you actually see light, you can see that photon coming out either in this direction or that direction. These are the two most probable directions. And why is that? It's a little bit more technical, why it's not coming isotropically. So now you see, basically going back to the same scenario, that you see 1 photon has scattered, 1 atom has scattered, come to another different spin state, and it has actually emitted a photon, which is coming in this direction. You take a single photon counter, which will respond to that photon, and you put it here, right? So at the end of the day, n minus 1 atoms are on this state and 1 atom is in this state, and you ask the question that is this an incoherent superposition or is this a coherent superposition, right? And that was the really insightful observation of Dickie, which people are still like, trying to understand all the consequences of what he talked about in 1954. But this is really, like people actually understood the consequences of all this over last 15 years, and this really set off this whole field of quantum information where actually people realize that these are amazing sources of quantum states. The point being that, so this is a cartoon again that, there are how many? 6 atoms. I'm just like 10 to the power 6, I've reduced to 6. So what it's showing, the red one, so all blue ones are one spin state and red one is another spin state. So this curve is showing the state of that atomic cloud after that one scattering event. So what it's saying is that you are actually not in an incoherent superposition, but it's actually in a coherent superposition of either the first atom made the scattering or the second or the third or and so on. And why is that? Because of the fact, and this is one very beautiful side of quantum optics, that this is what I call this, like pitch path information, that if you have no way of knowing which atom scattered the photon, you just don't have that information, and that lack of knowledge is what creates a superposition. So this is a very emerging field in experiments of actually creating superpositions and entangled states through projective measurements. Probably you have heard this technical term that, if you design a measurement properly, the superposition was not there before that, but through your measurement you have projected it. Because, like through your measurement only that much information you can know. So first and foremost, you see that this superposed state is actually, like it's actually an entangled state because, the nature of the state is basically, if I write it, so it's basically 1, 0, 0 plus, 0, 1, 0, 0, dot, dot, and so on. So, either the first atom has made a transition from state 0 to 1 or the second and so on. So, technically people call this a W state. It's just this obsession with English alphabets that you see that either this is up or that's up or that's up. So it's like a W. But in principle, it's a W with branches extending to like 10 to the power 6. And this is actually just a shorthand way of writing it. The way you should read it is that the ith atom, I equals 1 to n, is in the state F. So my notations are basically, I'm taking the state G, the state F, and then there's an excited state. So one of the atoms in the excited state, direct product with all all n minus atoms, direct cross product with that, and that's what this state means. So that's basically another way of looking at this, which is which is another very important point, is that you see that this superposition kind of remembers, so this atomic cloud actually, because one atom has gone there, it has become a memory. It's actually truly a quantum memory. It actually remembers that one scattering event happened, as long as, this superposition lives. So basically at a later time, you can actually extract that information out of the system. So this slide is just for people who are interested technically. So this is what actually Dickie proposed, which was a huge, huge surprise in 1950s. He again then wrote a series of papers in kind of late 1960s, which triggered experiments that basically he was saying that, you can actually make a mirrorless laser because, this system just has a coherent emission. And actually, it's just not limited to that one. If you just keep the light on and don't stop the light after one scattering event, you see that you start with all the atoms ground state, but then, there are all this like first one, then second, then third. Somewhere in the middle, the system is highly, highly entangled, and then you can actually go back eventually to all the atoms taking the ground side. You can actually drive the reverse process. But now the series of couple of experiments I'll talk about is actually effectively the same system, but this was actually done in a different lab. So this is actually the same atomic cloud, and except that when the photons are coming out, we also put 2 mirrors around forming a very bad cavity with a finesse of the order of, finesse as in how many times it reflects, of the order of 100 or 200. So just kind of what people, experimentalists will call a pickup cavity or a pickup signal cavity, where you just kind of raise the signal by that amount because the photons are bouncing back and forth and there is constructive interference if you're on resonance. So, so this is how it actually looks like, again, quite ghetto, that, like mirrors with piezos like glued inside a vacuum chamber, and then the action happens here where you trap the atoms, and this is a more fancier kind of cartoon of that. So, so now the question is, what happens in the reverse process, in the sense that, like when it's there, just now I said that it's a memory, so I can actually drive this process ulta, I can actually like make this like go from here to there, and I can actually get the photon back. And you can ask the question that what is that rate? Suppose this photon actually, this atom actually goes to the excited state, I turn on a laser which is resonant with that, and it comes back to there. Does it scatter at this? This is the same question I was asking in that second of that quizzes, that, what is that rate? And actually it turns out that that rate is just not the rate of that excited state lifetime, but it's actually n times that. N being, now if you have 1,000,000 atoms, the n is basically 1,000,000. So there's a tremendous, so that's why Dickie used the term super radiance. So suddenly you see this effect, though the atoms are not directly interacting, you or rather, someone opposed, they're not interacting with each other, they're all commonly interacting with the radiation field, in this case, that one mode that's defined by, the longest optical depth or the cavity. So you basically see that, so there the photon is like n times more, coming out n times faster, basically, and that's basically this factors of square root of n that was there in that normalization of that state, 1 over square root of n. So basically that fundamentally changes the effective dipole moment, and that changes the lifetimes and so on. So you actually see that scaling of the many body scaling, or of the fact that you have many particle scaling in that factor of. So this is another way of looking at that same thing just now I said, that when you are actually turning on a field to bring that atom back, you actually see that there's a field strength here, and then there's a strength here, which actually gets multiplied by a factor of square root of n. So this is like the quintessential signature, which otherwise you would say, oh, that's just a normalization, here, but that normalization is the signature that you are actually dealing with a many body state. And if you see this physics of coming back, besides the fact that there is a collective enhancement, it also has a lot of dark state physics. The reason that actually this can come back from here to there is because there are these two couplings, and there is the same dark state that I was talking about. So if you do it right, if you have the frequencies right, you can actually get the atom come from here to there, in the process emit a photon, but not scattering anything spontaneously. If you are more interested in this, there are a lot of technical details in this. But basically, if you're interested, we can discuss more about this part, that it turns out that it's emitting in one direction at n times faster, whereas all other spontaneous directions are suppressed. That suppression is really the signature of this collective excitation. And so this is exactly the state which is in the classical or low photon sense I was writing there. And here, basically, these things I'm keeping explicitly track of the excitation. So this is basically saying that only one excitation was there in F. There was nothing in the excited state. There was nothing in that optical mode. So this is a photonic mode. This is just like describing the excited state, that there is one excitation in the excited state, nothing in the photonic mode or light mode, and there's nothing in F. And here, it has come down, and in the process, it has emitted a photon, so there's exactly one photon in the cavity. So, so another way of looking at it, you remember when I was talking about this dark state, I was saying that, you can think of, if omega 2 is too large, it becomes all 1, or omega 1 is very large, it becomes all 2. So physically, you see that, if I don't have this field omega, the state is here, that's my starting state, and I can still think of this as a dark state. Because only this coupling is there, this coupling is not there. When I actually turn this on, you see that the excitation has moved from here to there, because now this is very strong compared to that. I can as well ignore this coupling. And as a result, you see that physically the state, as if it has rotated in a Hilbert space, in a 2D Hilbert space, which is equivalent to actually physically the atom moving from one side to the other. So what I would say, like maybe you are thinking that I'm talking of very simple things in like many different ways, but you will see that why as experimentalists we keep looking at the same thing in different ways, because sometimes it has very interesting non-trivial physical consequences. So basically this is the story that, the atoms could have otherwise emitted in free space, and they are coupled to this particular mode, which in that case is a particular single mode, which that case was a cavity, but it can also be just, if you have an extended sample, that very particular mode that you're defining, and this comes to the detector. So because this coupling has a factor of, it is enhanced, so this coupling will dominate over that, and you will actually always see a photon coming out, and that's the reason this has turned out to be an excellent single photon source and memory, like presently in the field, and people are routinely using this. So now, given that, like just going back to this point that, like actually turning on and off fields are equivalent to a rotation of a vector in a Hilbert space, which is equivalent to an atom moving from one state to the other. So the question is, can you actually extend it a little bit further? And that's kind of the experiment, because I think that's very relevant to the school. That's what we did effectively. We basically asked that, if we now play this game, not with one ensemble, but actually two ensembles. And two ensembles are coupled to one electromagnetic mode, at the same time, and we basically scatter one atom from one side to the other and try to see whether, there is a similar dark state physics in the case of two ensembles actually coupled to one mode. So it turns out that if you do that, what I'm talking about is that there are now two ensembles, macroscopic superpositions of atoms in two sides, coupled to one particular electromagnetic mode, and of course they're coupled to their own respective, free space. They can also just lose the excitation by scattering in the excited states. So it turns out that this, if you write down all the states, that it's not really a three-level system that we have been talking about, but it's a little extended because now you're considering another system. So it's actually forms a five-level system, which looks like that, this atom A, there's an excitation, this is its excited state. This is the mode where the photonic excitation is there. This is the mode where the excitation is in B, and this is its excited state, and they're all coupled. So it forms a five-level system. And this is just like, diagonalizing Hamiltonians, like finding eigenvalues and vectors. And if you actually, there's a very specific symmetry which you can generalize to like much, much higher order levels. It turns out that all these kind of structures, for a very specific reason, actually has similar dark states. So for example, in this five-level system, actually there's a dark state that forms as a superposition of this and that only. All these intermediate states gets decoupled, and the superposition is also counterintuitive, that, like this state is coupled with that field, and this state is coupled to that field. And these are basically just classical electromagnetic field that you can turn on. So if this is starting to become vague, you can keep going ahead with the example of the three-level system. It's basically just an extension of that. So now you can actually do the following game. You can actually write an excitation in the first ensemble, which is basically as simple as what I just talked, that you scattered a photon here, and you have nothing in B. So this is a completely spin polarized sample. This is basically, spin polarized with n-1 atom in one state, one in the other state. So this I am depicting as A, that there's one collective excitation, n-body excitation here, there's nothing here, and I actually turn on a field, just a classical field, here on atoms B, but you see that it's not going to see anything because there is no extra atom to scatter off, right? So it's kind of a meaningless thing, but why I'm doing that is because it actually defines a dark state. So now, if you actually slowly turn a field here and turn that off, the dark state being a superposition, suddenly it becomes actually a combination of this and that, and actually it rotates. Exactly the way I was talking about, you can visualize the other three-level system, simpler system as a dark state rotation. Here also there is a rotation. But now you see the advantage of looking at the same thing again and again in different ways, because now this rotation is just not something trivial which you can understand in many different ways, because you see that A and B are actually physically separated two large ensembles, right? I'm talking of atoms here and atoms there, so actually experimentally, this is the cloud of atoms. They are actually like two ensembles. They are separated not by like, not space-like separated, but nevertheless for experiments, these are massive separation, like 0.5 millimeter. And you can actually take images like it's normal CCD camera, security camera images, and you can see the samples like separated out. They are largely separated. And you are basically playing these games with these knobs, which are just classical knobs, like classical fields. You're turning them on and off. And basically that's what first we saw, that you have one single atom on the other state in the sample A, you have this field, now you turn both of them on, these are the actual time traces, this is actually now, this is all the way, and you see that, like, this is what we expect, so this is the experiment actually. You see that, so this is the time where we actually do this, turn this both of them on, so there is some leakage of photon, and this is when we actually turn on, so this is a region where all this transfer is happening. So we actually turn one on, turn the other off, and then we wait because the excitation has come to there. So now, if things are right, then you started with n-1 atoms in sample A on pointing downwards, one pointing up, and all of them here were pointing down, and you just turn on fields like that, and now this has all become down. And that should have come down, so come up, like, right? So there, if I now turn on another field, I should see that coming off as a photon. And that photon should come out n times faster, very well directed. And that's exactly what we see. So in this trace, you can see there's an effect of memory that, we are turning on later. So, like, whichever time we turn on later, you see this pulse, which is actually a single photon pulse. And one of you asked that question, what is meant by single photon pulse? So this is actually a single photon pulse, which you can think in terms of histogram, that it's basically, time traces, these are basically just the pulse basically means that the probability of, if you repeat the experiment a million times, different time, this is just a probability curve, basically. And they're coming out at different times, right? So now you can basically ask this question that, what happens? This transfer is basically in my hand, right? I'm actually slowly turning one on and turning one off. But I can actually do something else. I can say that, I'll not transfer completely. I'll basically start turning this on, turning that off, and halfway I'll turn off both of them. Then what happens? There's only one excitation, right? It's exactly like that photon falling on a beam splitter. It can go this way or that way, right? And one of you actually said, I think I have that written, that actually if I write down the state, if I see the probabilities, they're 50-50 coin tossing. But if I write down the state for that beam splitter and the photon, it's like that. Right? So I should exactly have that here, right? So, so basically, that's what this last half is, that, if we actually stop the transfer somewhere in the middle, you see that these are actually, it should go into a superposed state, and with one, either the excitation here or there, these are the probabilities. In case of the photon and the beam splitter, these were half-half, but in these cases, you can actually control these probabilities by choosing your turn off time, and there are details of the angles and so on. But at the end of the day, you go ahead in the lab and say that, does it exist? Is it superposition again? So you basically actually need to change that phase again. So that's like, otherwise you cannot prove that it's a coherent superposition. And that's what we do in the lab, or we did in the lab. This is kind of an old experiment. We actually, when we start changing the phases between these two classical fields and try to see how they're coming out, you see like perfect sinusoidals. So this is something, like really exciting for experimentalists, because you are actually seeing like two macroscopic samples. They are in W states. So, they're actually like states like that, a many body state. And as you change the phase between them, you see that these two macroscopic samples that you can see naked eye are actually interfering like this, right in front of you. And that's this thing, and the visibility is very high, 88%, and you basically can characterize the entanglement. There's something like the concurrence and so on. You actually show that they're truly entangled systems. So, so basically, that's that. And then, so this is basically in the single excitation regime with million atoms of two samples physically separated and interference. But still the question remains that this is effectively one excitation, but with million atoms. So it actually opens up a question that for this kind of Dickie superradiance, where what are these states? Is it like a single particle state? It's clearly not single particle because all over the place you see signatures of the many particle effect. So basically, in Angelo's curve, coming back to this, and this is still messed up, where are we? And the question is, in this kind of effects, like where would this kind of experiments be? And actually to be somewhere in the middle, to hit the middle, how many atoms do you need? How far do you need to come down in the Dickie ladder to actually see, be in this regime? So that's kind of my motivation of attending this school, right? So that's also what I'm trying to learn. So I have only like 10 minutes or so, but any questions up to this point? Not making sense? Yeah. Yeah, it's scaling with the number of atoms. So you basically set up your detector, you see the rate at which the photons are coming, you know what is the rate for a single atom, and that is what you would have expected, but you see that it's scaling with the number of atoms. And you change the number of atoms and you see the rate changing. So those kind of like studies of super radiance and scaling with n and so on. So this person, Harosh, actually, before he got into the person who got Nobel Prize a few years back, he actually, before he went into this superconducting this Rydberg atoms in superconducting cavities, or optical cavities, but RF cavities. Before that, he has like really interesting papers in late 1980s, mid 1980s, actually just studying the nature of this n scaling. So in fact, at this single excitation level, you see it scaling as n, but at middle of somewhere in the Dickie ladder, when you have put many atoms, you see it scaling quadratically. So it's a very, very strongly linear. Yeah. So basically now I'll quickly change gears if there are no questions. And this is basically, yeah, sorry. They're not really intensity. We call them something called we call them Rabi frequency. If you want to think of them, there's by a factor of 2 depending on which school you belong to, but it's basically the intensity times the dipole moment between the two states 1 and 2 divided by h bar. So it gives a frequency scale. That's why we are writing it as a so you can actually see that, this has the field strength. So, the E square will be energy which will have the number of photons. So it's scaling as square root of the number of photons. So it's scaling as root n. Root n, where n is not the atoms, it's just the number of photons. So if you go to like, no photons, the fundamental omega 1, or for vacuum, the omega 1 you get is what is called the vacuum Rabi coupling. Yeah, but basically, everything I talked about in that classical example is, if you're thinking in terms of the number of photons, you should basically think about this electric field E to be in a state which is a coherent state, which is basically a superposition of like infinite number of photons. So basically, I'm talking, you remember I was talking about the relative phases between omega 1 and omega 2, so they are classical fields. Or quantum mechanically, they are coherent states, so they have phases. Right? So basically the number of photon, the sense of number of photon has been washed out. And that's what defines a well-defined phase. Right? So they are effectively coherent states. And if you do that, so then this E becomes basically the strength of the coherent state. Yeah. So, but that was purely for one atom case. Infinitely many super. Yeah. Yeah. No, it's, well, maybe we are notationally getting stuck. So there are two things. Are you talking of the frequency omega 1 and omega 2? Big omega. Yeah. Yeah, so this is basically, no, you see that whatever omega 1 and omega 2 you have, that defines your coupling, and for each of those coupling you have a dark state. So dark state is basically defined by the coupling Hamiltonian you have, and that you can write it in that form, that a specific combination is coupling. So for each of those combination, for whatever omega 1 and omega 2 you have, everyone has a corresponding orthogonal state, which is the corresponding dark state. So you give me an omega 1 and omega 2, or 2 electric field strength, I'll give you a dark state, which I'll just write the orthogonal state. But if you are asking about frequencies, then the frequencies needs to follow, and that's because of, like, you can argue many different physical ways of energy matching conditions and so on. The frequencies are fixed. You don't have an infinite combination of frequencies. Frequencies are fixed, yeah. And because that also shows it's a single atom phenomenon, basically. They're set by the atomic. So there is an infinite family of, if that's what you, right? Another dark state. But for a given omega 1 and omega 2, you always have a dark state. And that's why, the other things I was talking about, that's actually in the range where omega 1, omega 2 are not even coherent states. They are actually goes through a Fock state or single photon state. And there also you find the dark states. Yeah. Mm-hmm. Yeah, that's like very naively, that's what open quantum system means, that like it's open to other states which are not accounted for, and the energy can like leak out. Yeah, so it has a very strong effect of difference. That's the whole notion. Yeah. So from those curves, from those traces, and we can talk, actually it's quite technically involved, we can talk in more details, but those traces actually have explicit signatures of those time scales. So this is something in a very different thing, but this is also something we have been setting up for last like few years, is actually what you are seeing is the raw, again, a ghetto experiment setup of, this golden thing is actually a little tiny vacuum chamber, not very good vacuum, and inside there is a very fancy device which is basically a single atomic layer, which are called graphene, you have probably all heard of. So that's basically hanging so there is a whole, you should think in terms of drums or tabla, that it's basically like a drum, so there is a membrane which is hanging, and then there is a metal below, and this membrane basically can oscillate and so on. And that's what is there inside this little, like, these blue lines are basically very, like, pumping lines, very rough vacuum. And these things are stages which can move the membrane back and forth, and this entire structure is actually a microscope, a home-built microscope to probe, the motion of this membrane. And then there are this, there's as if like there's a ground floor and first floor. This first floor is basically forms something which, so this is how we probe, and the first floor actually forms something which is a Michelson interferometer. So I'm assuming that everyone, since I'm also running out of time, I guess, yeah. So basically, everyone is familiar with LIGO. In principle, this measurement setup is exactly like that, though it's an extremely crude and baby setup of that. But it's basically, instead of trying to detect such small things as gravitational waves, we are basically trying to detect vibrations of a single atomic layer. And for that, normally we'll not see anything. So we basically try to magnify it by interference, and interference you can do it in different ways. Either you can do it within the sample, or you can actually do it through this Michelson interferometer. So this path actually gives you a phase reference, and also the amplitude of this path acts as an amplifier. If you think of the interference terms, there is like E1 and E2. So even if E1, the scattered light from a single atomic layer, might be very small, if E2 is large, that kind of like boosts up the power. So that's the thing. These are the drums. The drums are actually made. So this samples are made in Max Planck in Germany. So this is how they from top look like. You know, there are different drums of sizes, and they are actually covered with something. This is a cartoon of how this single atomic layer look like, carbon atoms. And this is another picture from a different system, but this is effectively the case that, you know, this is a graphene membrane, and it's actually like hanging there, and there's a below conducting plate. Graphene is also a good conductor, so if you actually put a voltage between them, you know, like, so you can actually form a capacitor, and as you put the voltage, what happens, you know, there's a capacitance of it, but more importantly, graphene is also elastical. It has very interesting properties, so it actually just gets stretched because, you know, it feels a static pull, it gets stretched like a balloon. So the meaning of this, for as far as vibrations are concerned, is that you have a drum which you can tune. You can tune the frequency of it. So I'll really just tell you what we are doing. I see I have 13 seconds left. So so this is how the images in that crude microscope look like. So this whole red thing, this axis is intensity. This is just a surface scan. So these blue parts are the substrate, which is silicon nitride, and this red part is basically no light is coming out almost. That's graphene. If you actually focus on graphene, you see that actually there is light, very weak light, but that has like these undulations, you know, and like folds and so on. And then we do a very simple experiment. We first basically send in a light. Can I get like 5 minutes? So we send in a light, just a DC, you know, like light, and some very small fraction, I should not have put the same color, a small fraction, 10 to the power minus 5 photon, like, you know, 10 to the power minus 5 parts of it actually gets reflected back. So we actually look at the reflected light, and ideally, we should have expected that, you know, like this is a DC electromagnetic field. We look at the reflected light, we put it in on a photodetector, and we look at the Fourier transform of the current. And if it's a DC light, we should see that the Fourier transform is flat because nothing is moving. Right? But that's not what we see. We actually see that, you know, like there are this very nice, interesting spectrum. It took us for a while to understand it, but actually what it's going on is that actually this graphene is doing Brownian work. Except that, you know, so basically just thermally it's jiggling, except that, you know, it's bound, so it's not a free particle Brownian walk, and as a result, it can only do the things that are allowed by its boundary conditions. So this is something straightforward. One can solve a circular membrane for the circular boundary. These are just Bessel function modes, and that's kind of what we see. There are some additional complexity. There are kind of interesting splittings because of anisotropy and so on, but those are details. But so let me just quickly go to where superposition is coming in. So it turns out that this is not the whole story. The graphene is actually placed on the silicon nitride, which is a substrate. But it turns out, and there will be many talks this week on optomechanics, it turns out that silicon nitride is also a great mechanical resonator, you know, and we have a 250, 300 nanometer thick silicon nitride. So if you actually excite that whole substrate can also start oscillating. So you can actually think of that's why I was giving the example of tabla or like a drum with a head in the middle. So as if there are like two membranes, two oscillators. One is the middle graphene and the outside whole substrate can vibrate. So actually, if you see the substrate modes, the substrate is very heavy. So actually the displacement of the substrate, by the way, just to point out that these displacements are of the order of picometers, you know, like, so these are way, way smaller. So these are like way, way smaller than the thickness, so the atomic displacements, basically. And this kind of displacements we can measure because of the fact that, you know, because of this interferometer. And if you see, it's not surprising, LIGO is measuring like 5 orders of magnitude below us, actually. So the substrate is much heavier. The displacement scales inversely as the square root of the mass. So actually, they should be like, you know, femtometers of the order, 100 femtometers or so. So you don't see the substrate, but you can explicitly drive the substrate modes, you know. And when you do so, you see that within the same frequency range, and this is actually driven, so this is not a surprise, you see that there are many, a zoo of substrate modes, which basically says that if you hit those frequencies, you will actually get the substrate going. So, and you see that in between, you can see this graphene, which are like much broader. So, so just a quick point that, you know, this is a graphene mode. Normally, again, if I go back to the earlier experiment that, you know, if we just look at a single the Brownian motion, we don't see anything in the substrate, but by driving it, we know where the substrate modes are. So we know where the frequencies are. And the nice thing about graphene is that, as I was telling you, that it's tunable, because you can actually like tune the frequency of the drum by actually pulling it, so you can actually get it from here to there, you know. So basically, you put a gate voltage and you can actually pull it from this point to a point where the substrate mode should be there. Why you should pull it? Because in that case, you actually have now two oscillators which are actually interacting with each other. When we do so, we see, oh, I should just stop. Yeah, so we actually see something, like very, very interesting. We exactly see that there's an interaction and the traces are exactly the similar of that of, in fact, these mathematical functions are exactly the same as that of those dark state splitting, here that we are showing, which indicates that, there is actually like, these are superposed modes, but they are not superposed modes in the usual sense. They are actually superposed modes of a phonon in the substrate and a phonon in the graphene. And that actually, the meaning of dark state here is that, where you would have expected the maximum resonance, you actually see that there's a complete suppression of oscillation. So if you actually go ahead and look at this point in graphene, you see that it's very, very quiet. It's quieter than what its thermal fluctuation. So that's where I should end. Yeah, so basically the conclusion is that, so the question is, this kind of systems, how much of it is macroscopic, and then basically, like the superpositions, whether they carry additional key of, the validity of the way we understand quantum.